Good afternoon and welcome back. I am Nicola Seriani from the ICTP, and I will chair the first part of the afternoon, the session of the first part of the afternoon. So let's move back first to directly to the first talk that will be given by Dr. Mustafa Genisel from SESAME. So Mustafa Genishel, he's received his undergraduate degree from the Middle East Technical University and a doctoral degree from Bilkent University in Turkey. And before joining Sesame, he was a faculty member at Dicle University. So his research focuses on characterization techniques and hard coatings based on physical vapor deposition. And now he is at Sesame in Jordan, and he's the head of the HESEB soft X-ray beamline there. So, and he will talk about that now. So, Mustafa, please, the stage is yours.
Thank you very much for this nice introduction. Good afternoon, everyone. Let me share my screen with you, my slides with you. Now, I hope you can see my screen, full screen. Can you?
Yes. Yes.
Okay. Okay, first of all, thank you to attend this meeting. Thank you in the beginning. Thank you for your patience. I have a problem. My throat is not good. I can drink some hot water. Sorry for this. Okay. First of all, today in this session, I'll give you brief information about HESEB beamline and its end station. HESEB beamline is an soft X-ray beamline in the SESAME. Here is the outline of my topic. In the beginning of my topic, I'll give you information about HESEB project, what is HESEB project, what is HESEB beamline. And in the second part, I'll mention about what is soft X-ray and X-ray absorption spectroscopy. I'm sure most of you know this. Someone is raising her hand. I don't know. We will maybe we will answer it at end of the speech. And in the third part, I'll give you information about HESEB beamline. In the fourth part, the HESEB end station and soft X-ray absorption spectroscopy. First of all, what is HESEB? HESEB is actually the abbreviation of Helmholtz SESAME Beamline project. It's a soft X-ray beamline project. This project is funded by Helmholtz Association. There were 5 Helmholtz Center in that project. SESAME is the partner of this project. And it is the first soft X-ray beamline in SESAME, and it is it has the first undulator in the SESAME. We made an inauguration in 2022. Yes. So let's look at the typical X-ray spectroscopy beamline. We have a photon source, then we have a monochromator, and we have an end station. In HESEB undulator, we are using an undulator third generation X-ray source as an X-ray source. It's an Apple II type undulator. It is its name. It's UE56, and as a monochromator, we are using a planar grating monochromator. It has two kind of gratings. One of them is 400, and other one is 1200 groove in millimeter. And after monochromator, we have 2 branch. Actually, we have 2 end station. We call them sisters beamlines because their mother and father, their photon source and the monochromators are same. One of them is we call it ID11 HESEB end station. It's an absorption fluorescence end station, and the other one is ID11 right R. It's text-based photoelectron end station. My colleague Zeynep will give information. Dr. Zeynep Öztürk will give information about text-based after me. And here is the plan view of HESEB and text-based together. Again, first we have an undulator. After undulator, which is inside the tunnel, we have an M1, cylindrical M1, which makes the beam vertically collimated, which is needed for PGM. And outside of the wall, we have an planar grating. We have a monochromator with two different kind of gratings mirror, and after grating mirror we have M3. M3 has two mirrors. It contains two mirrors. If we put M3A in front of the beam, it will direct to the beam to the left. So HESEB, as I mentioned, ID11L. And end of this, we will focus the beam in here. And after that, we have a refocus mirror. And at end of the HESEB line, we have an HESEB end station. If we put M3B in front of the beam, we will direct the beam to the right, sorry. And at the end of this beam line, we have a TechSpace end station. So again, HESEB and TechSpace are the sister beam lines, and because they are using the same undulator and monochromator. So let's look at what is soft X-ray. If you are not familiar with synchrotron radiation, maybe you first time you heard about the soft X-ray. Here is a very well-known electromagnetic spectrum. Actually, we divided into sessions with respect to their interaction with the materials. And when we look at the region and interaction with the materials, we have a microwave, which is dealing with free electrons. We have microwaves, which is dealing with the rotations, and infrared with interaction with the vibration of the motions in the molecules. And we have visible and UV light in here. It's dealing with the valence electrons. And X-ray is dealing with the core shell electrons, which belongs to one atom, mostly belongs to one atom. It's dealing with these electrons. And gamma ray is dealing with the nucleus. It's interact with the nucleus of it. As you see, there is no soft or hard X-ray in here. But when we close look at the high energy part, X-ray is divided into soft X-ray and hard X-ray. Soft X-rays are the X-rays with lower energy, bigger, longer wavelength, and hard X-rays are the higher energy and shorter wavelengths. But at the end, from interaction point, both of them are interact with the core shell electrons. So why we need an division between hard X-ray and soft X-ray? It's mainly because of their optical elements are different from each other. Because of that, we have different beam lines as soft X-ray beam lines and hard X-ray beam lines, because their energy, their wavelengths is so different that we need some different kind of optical elements. Maybe you heard it from the other talks. And mostly we are putting these limits, but when we say soft X-ray, we mentioned about the 200 eV to 2000 eV. So the wavelength is changing from 6 nanometer to 0.6 nanometer as a wavelength. So when we look at the tabulated spectrums, these soft X-rays between 200 and 2000, it's getting interact with the, when we look at the tabulated data, it will interact with the low Z materials. As you see, hard X-ray regions start from 5000. So after titanium, you can you can make the characterization. If your element has a lower Z or lower atomic number, lower than titanium, you cannot make an X-ray absorption in hard X-ray absorption spectroscopy beamline. But what about for low Z materials, for carbon, oxygen, or nitrogen, this kind of things? So soft X-ray is in that region. So soft X-ray is mainly interact with the carbon, oxygen, nitrogen, which are also important for the industry, which is important for the life science. And when you look at it, also it's interact with silicium. Silicium is the heart of our electronics integrated circuits. Yeah. And also it's interact with the L shell of the materials. We will go deep inside later in this presentation. So let's look at the interaction of the photon with the material, X-ray photons with the material. And let's look at this is our incoming photon with an specific energy. When it's interact with the material, either it will transmit it, maybe it lost some of its photons. It will reflect it. which these are reflection is not our case now. Or it will absorb. When it's absorbed, after some process, it will emit photons with different energy, or it will emit electrons. Again, we are talking about ionizing photons, X-ray photons we are speaking, or it will scattering. Reflection and scattering, scattered photons are out of our scope, but we will directly look at the absorption. So let's look at the X-ray absorption. What we mean, it will interact with the core shell electrons. Here are the schematic representation of what we mean core shells. In an normal element or in a compound, the element has fully occupied shells, which are mainly belongs to the atom, and they are fully occupied. We name them with K shell, L shell, or M shell. And we have frontier orbitals, or from chemical perspective or for molecules, we can say that LUMO and HOMO. And we have, if we are solids, we have conduction band or valence band. Valence band is full with electrons, and the conduction bands are empty. Over that, we have a continuous phase, and after that, there is electron is not bounded to our sample. If the energy of the photon, which has an energy, is related to, it can take electron from, for example, K shell, and it can transfer to the conduction band or LUMO, or if it can emit the electron from this, we can say that our X-ray is interact with our core shell electrons. Let's look at the absorption phenomena. Here is again another version. Core shells are occupied with electrons, and here is the graph. When we send a photon with a specific energy, let's say that here is the energy of the photon. This sorry. This is the size of this, the scale of this is represent the energy of the photon. As you see, there is no electrons in here which can go from here. So it is mainly not absorbed by our sample. So our absorption is low. The photon will transmit it from our sample. So absorption will be low. When it reaches certain energy, for example, the energy of the photon is the energy difference between this and here, it will start to absorb. And when we increase it, it will continue to absorb, but the absorptivity will decrease with the increasing energy. And when it's reaching certain energy levels, which has we can compare it the energy of the core shells, it will again absorb, and it's going on like that. So in each these step ups, we call them edges. And when we say edge, we mean that we have an full occupied orbitals in that energy range. And we have K edges. K edges represent the 1s electrons in the 1s orbitals. L edges deals with the electrons in the 2s and 2p orbitals. In here, the L and M and K names come from the main principal quantum number, and it's going on like that. So when we look at it, we have absorption edge. When we say K, it's electron excited from 1s orbitals. And when we say L, electrons are excited from 2s orbital or 2p orbitals, and it's going on like that. And when we look at the HESEB, we will deal with this later, but anyway, we will go deep in here. But when we look at it, HESEB is deal with the K shell of the beryllium to the aluminum silicon, and from silicon to the krypton, L edge of the silicon to krypton, and M edge of these second row transition metals and lanthanides. There are some limitations. Even we said that we can look at the M edge of these materials, but it is scientifically they are sometimes not give a good data because of some restrictions. Okay. From now on, we talk about what's soft X-ray, what's happening, what's soft X-ray absorption spectroscopy. And let's go to our instrumentation. I will just give a brief information about the HESEB beamline. As I mentioned before, we have photon source, we have monochronometers and end station. So what's our photon source? Photon source is undulator. It's an Apple II type undulator. You can see the picture of it in here. And in here, you can see me. I didn't put just to show that how I am handsome. It's just to show that how it is an huge equipment. It is more than 9 ton, and in here you can see the picture from side, and you can understand why we call it ID11. ID means insertion device. We insert this undulator between two bending magnet 10 and bending magnet 11. You can see in here. So we put this undulator between these two. So it is insertion device, and it is just before the bending magnet 11. We call it ID11. So when we look at also what is the advantages of the radiation source of HESEB, you can see in here the other X-ray sources. First, the X-ray tube. You are common with this. We are sending electrons and it's emitting electrons, but it's not diverging. It's diverging. It's not converging. Its flux is low. And when we look at the bending magnet and Wiggler, they are continuous source. Their intensity is they have some intensity, but when we look at the undulator has a diverged beam, converged beam, and also it's acting like a line source. So in specific photon energies, the intensity of the source is sometimes 10,000 times higher than the bending magnet. So it is the power of undulator. So it's the power of HESEB. HESEB has the highest intensity in specific desired photon energies. Why we call it Apple? Apple is not just apple to eat. It's actually abbreviation of Advanced Planetary Polarization Light Emitter. It's Apple II type. The idea is Apple they can produce not only the horizontally polarized light, not only the linearly polarized light. Also, we can produce circularly polarized light, which is important for circular XMCD, X-ray magnetic circular dichroism measurements. So here are some properties of our undulator. We can go down minimum 70 eV. And here you can see the harmonics. As I mentioned before, undulators are different than the Wiggler or the bending magnets. They are line source. You can see some harmonics and some orders from these harmonics, which is collected from HESEB undulator. This is in some specific energy, intensity is so high. So what are the properties of HESEB beamline? If we compare with also the monochronometer, the energy resolution is better than 8000, and it has two grating mirror, and it can work linear or circular polarized light, and photon energy is between 90 to 1800. And it's almost cover whole periodic table except hydrogen, helium, and lithium. The flux density on the sample is 10 over 12 photon per second, and spot size is 100 half millimeter to quarter millimeter. But we have an optical capillary. I'll mention in the further part of the presentation. We can go down to 60 to 40 micrometer in the spot size. Here is the photon flux on the sample. As I said, it's around 10 over 12. With the energy, when we increase energy, the energy of the photon flux will decrease, but it's still in the range of same magnitude. So we give information about our photon source and monochronometer. At the end, we have an end station. as I mentioned before, end station, the soft X-ray, it's to complete deal with the low Z materials, as I mentioned here. But when we look at carefully, carbon, nitrogen, oxygen, and argon is in soft X-ray regime. Why it's important? If you look at carefully, they are also the component of the air. So it's sensitive to air. It have to require vacuum. For example, in hard X-ray, you don't need a vacuum. Air will not absorb that much, but dramatically decrease the amount of photons will decrease if there is if we make the measurements in air. So we need an ultra vacuum environment. Here you can see our end station. We have this is our analyze chamber. This is our vacuum section because, as I mentioned, we need an vacuum environment, and we have a motorized manipulator over it. We cannot move our photons, so we have to move our sample in front of the beam. Here is another view of the end station chamber. And here in the right part, you see the beam path. Photon beam is coming from here. They are showing the same thing, but the angle is different. And here is the analyze chamber. And we have a load lock. At the end, we are working in ultra vacuum environment. In each case, in every sample, I cannot open the analyze chamber to the air. It will take some time. So what we are doing, we are loading our sample in load lock, and we are putting in it. And we have fluorescence detector. I'll mention later why we need it. Here is our magnetic transfer arm and our load lock. We will put, you can see in here, our sample with an arm. With this arm, we can put our sample without opening our analyze chamber to the air. So here are the properties of HESEB end station. It has a fluorescence detector, XRF Bruker flash detector. It has a Keithley calorimeter, which needs why we need it because of electron yield measurements. I'll mention about them. What does this fluorescence yield and electron yield? And we can cool it our sample with liquid nitrogen. We can heat up our sample up to 800 degree. We have a magnetic stage. I mentioned about that. It has a motorized sample holder in 2D mapping, elemental mapping. We need this. I'll show what kind of data we can obtain from this feature. And we have a differential pumping ability. We have an optical capillary. We can make a differential pumping, which is important for sensitive samples like historical samples, and we can make measurements in different atmospheres like catalyst research. I'll mention these things in a few minutes. Okay, let's look at this the things the soft X-ray absorption and material on the material from HESEB perspective. Here is again it's our incoming photons. And here is the transmitted photons. In this case, this is what we classically know that we are looking at absorption. We are comparing the intensity of the incoming photon with intensity of the go through the photons, number of photons which go through our material. But it is not common in soft X-ray techniques because it needs really thin films, nanometer thickness of the films. So instead of that, can't we make an absorption? No, we can make, because when soft X-ray is absorbed by our materials, after some progress, I'll mention in a few minutes, either it will emit some photons, so we can use an XRF detector for this, and we call this as a fluorescence yield, and we can make the measurements. And HESEB has Bruker detector, as I mentioned before, X-ray fluorescence detector. It is a silicon drift detector, SDD, and it is not only the counting the photons. Why it's important? Why SDD detector is important? It's not just counting the photons, which is emitted from our sample. Also, it can analyze their energy, which is important. And or when soft X-ray is absorbed by the material, it will emit electrons. Again, this X-rays has ability to ionize our sample, so which means that it will emit some electrons from our material. And when electron is emitted from our sample became positive. If we connect our sample to the ground, and if we make the measurements of the drain current, we call it total electron yield measurements. And we have for this, your sample have to be conductive. For this, HESEB has Keithley picoammeter for this reason. But if you want to look at the kinetic energy measurement of the emitted electrons, it is photoelectron spectroscopy. It is out of scope of HESEB. It is text-based. It's the idea of text-based. My colleague Zeynep will give you information about this part. So let's look at the what's going on inside the material when we send when it's interact with the material, when it's interact with the soft X-ray. Here is the orbit. Here you see some orbitals. The dots are representing the electrons. And occupied states, these are the core shell electrons. They are occupied by electrons. And there are unoccupied states about the Fermi level. When photon absorption happens, which means that we are sending a photon which can take electron from core shell to the upper shells, absorption will occur. So photon will disappear. So now our material, our element became excited in excited states. Normally in hard X-ray, they can understand this from the difference between the intensity of the incoming photon and intensity of outgoing photon. But again, we cannot. This is not working in soft X-ray because photons cannot pass through the materials absorbed by materials. So what is going on? We are chasing other things. What's going on with absorption? When absorption occurs, it needs a relaxation. There's an empty orbitals, and nature don't like the empty things. So in order to fill this empty place, an electron from the above, from higher orbitals, higher energy orbitals, they will drop to the core shells, and when it happens, it will emit photons. And this is a fluorescence photon. It is specific for our element because the energy difference between the empty orbitals and the energy difference is well known, and it's element specific. And from this we can make the measurements, element specific measurements. And this is fluorescence yield, and we call it electron yield. At the end, as you see, we have one empty state. If we are scan the emitted photon energy, we call it absorption emission spectroscopy. Maybe you will say that, okay, in the beginning you said that we are looking at we have a silicon drift detector. We can look at the energy of the photons. But this silicon drift detector's energy resolution is low. If we use a high energy resolution, which is another beamline actually, when you compare it HESEB, and it's an we can make an absorption emission spectroscopy. But when we do this together, we can look at the get the picture of full occupied states. And or during relaxation, not only the fluorescence will occur, what will occur during relaxation, maybe our material will emit an Auger electron instead of photons, and energy electron will be emitted from our surface. So sorry, these are wrong. Sorry, these are wrong. Why it is wrong? This fluorescence yield. Sorry. I just realized it. Sorry. Yes. And we have two empty states. When it's happened, we have two empty states. And if you look at the energy of the electron, it's an origin electron spectroscopy. Again, we need a conductive sample for this. And here, relaxation, beside the vibrational relaxation, thermal relaxation, fluorescence yield and electron yield has a competition. Here you see the fluorescence yield with respect to atomic number. The problem about fluorescence yield in soft X-ray, the fluorescence yield is low if you compare it with the total electron yield. But these are obstacles, and we are overcoming this. I'm giving these details to show you the general picture. And let's look at the probing depth comparison. At the end, the materials absorb our X-ray, but the obtained X-ray, fluorescence X-ray, and obtained electrons depth is different than each other. As you see, when we are making the measurements with fluorescence yield, we are collecting data from deeper part. But if you are making a total electron yield, it's a bit more surface sensitive. I just put the XPS, probing depth of XPS, in order to give you as a comparison. But in here, you have to be careful about this depth depends on the energy of the incoming photons and electron density of the material and the energy of the emitted electron or photon. And polarization dependent X-ray absorption spectroscopy. Also, we can do this in HESEB. Here is in the left part. This is the core shell of the carbon 1s, and here is the empty orbitals, pi star orbitals and sigma star orbitals of an aromatic ring. In here, as you see, the sigma star antibondings and the pi antibondings orbitals directions are different. Let's say that this here is we put this aromatic ring on an single crystal which has specific surface, and benzene. These benzene or aromatic rings are parallel to the surface. The main body, the molecular planarity is parallel to the plane of the surface, and you see pi antibondings are perpendicular to the surface. And when you compare the angle of the beam with respect to these orbitals, if it is not interact with the pi orbitals, you cannot see the pi orbitals in here. As you see in here, the polarized photons are coming perpendicular to the surface, and this electronic transition, the electromagnetic electric field is not interact with the pi orbitals. We cannot see the effect of pi antibonding in here. But in sigma orbitals, we directly see in that case. So we can make a polarization-dependent X-ray absorption spectroscopy. For example, next February, we have a user who wants to understand the orientation of their molecule by this phenomena. So, as you understand from previous these pictures, you remember, this is a schematic representation of orbitals. We are dealing with the conduction band or LUMO. Soft X-ray absorption is mainly related with electronic structure. It gives us the picture of conduction band or LUMO, which is very important for photovoltaics, which is very important for batteries, which is very important for catalyzers. And it's surface sensitive, we can use this in these critical areas. So in general, if you look at the whole picture, soft X-ray spectroscopy, first of all, it's element specific. As I mentioned before, we are dealing with the core shell electrons. Core shell electrons are element specific, so we are make the element specific, and especially it's focused on light elements like carbon, nitrogen, and oxygen. And it is give us a picture of first row. It's working very well with first row transition metals, which are the important elements in all industry and for magnetization. And F block elements are working very well, especially lanthanides. And secondly, soft X-ray absorption spectroscopy is surface sensitive. As I mentioned, previous picture, previous schematic representation, it is the deepest data you can collect is 100 nanometer. And if you add the X-ray, XPS, and in total electron yield, we are really looking at the most of the our material, layer of our material. And I want to make an differentiation between hard X-ray absorption spectroscopy and soft X-ray absorption spectroscopy. Hard X-ray absorption spectroscopy are dealing with the fine structure. It gives you the picture of your element, the nearest elements. It gives you the distance between the elements, the electronic, the mass of the elements around your element. But in soft X-ray, it gives you the electronic structure, as I mentioned in my previous slide. But people are coming and asking me this question. Quantitative analysis, no, it's so complicated. Making a quantitative analysis with soft X-ray absorption spectroscopy, I cannot say this. It's so challenging, so challenging. So we give a brief information about soft X-ray, HESEB related soft X-ray absorption techniques. And let's go back to our end station and look at our sample holder. This is our sample holder at the receptacle part. It is normally vertical, but in order to show you in a better way, I put it in horizontally. Here is our liquid nitrogen reservoir. We can fill our sample in here with liquid nitrogen. And this is our receptacle part. And this is our sample holder. It's a sample holder. It's 14 times 40 millimeter active area in here. If you have a bigger sample, get in contact with me. And as you see, it is the nearest stage to the liquid nitrogen reservoir. This is a low temperature reservoir. In here, we have an electromagnet. I'll mention the properties of it in a few minutes. And it's a magnetic stage measurement for XMCD measurements. And we have a heater, button heater, for high temperature measurements. At the end of our receptacle part, we have a photodiode, which is not related with the users, but it is for diagnostic tools. It's a diagnostic tools we need it. What kind of samples? What type of samples we can make a measurements? Thin films, it's working well, and powder. And if you have a crystal or bulk, and solids, we can look at it. I'm sorry, if you have a low volatile samples, we cannot put it because at the end we are looking at we are making our measurements in ultra vacuum environment. And I mentioned about the optical capillary and the first in the beginning a few slides before previously. And here is what does this mean? Here's a schematic representation of the end station, HESEB end station. In here, this is our chamber. We have some valves and pumps and vacuum chamber. We have a couple. We can put a capillary in here. Here is the beam is coming from here. Before our chamber, we have a front end and we have a pumping unit. And we have a valve in here. This valve is a special valve. It's not a complete valve. It's a gate valve with window. Why it's important? When we close this valve, even we close this valve, when the photon go through this valve, and it will hit our optical capillary. Optical capillary, the diameter of the optical capillary is 20 micron in that part, 20 micron, which is so small. Even we fill this with gas, for gas molecule, it's not easy to go through this area. Even they came here, we have a gate valve in here. We are not allowing gas molecules to go through to our beamline, and we have a pumping unit, so we can make a measurement under helium. Why helium? Because other gas molecules, maybe you remember, absorbing the soft excess. So under helium atmosphere, we can make a measurement. And in here, we can focus the beam 5 millimeter after the tip of the capillary. So the path of the beam is so small in the helium, so we will not lose the photons in this atmosphere. And we have a fluorescence screen, so we can make measurements in that conditions. We can make total electron yield. We cannot make total electron yield when it's filled with gas, because the electrons which are emitted from surface will hit the photon other atoms, and we cannot make the measurements. So we have to make an fluorescence yield measurements in these circumstances. And when we fill the chamber up to 1 bar with helium, and the vacuum, the pressure in here is less than 10 or 12 millibar with the help of this pumping unit, and this gas will not affect the beamline, which we have to protect it. So here, how we use optical capillary. This is from a beam time. In here, optical capillary size is that much. Vertical, it's 40 micron. It is horizontal, it's 60 micron. And here is the beam size, vertical and horizontally. As you see, we can put our sample in front of this capillary. Here is, you can see, when we look at the nitrogen edge, and when we look at the carbon edge in here, you see the carbon is more than the other elements, and you can see for example, when the element is getting higher and higher, it's getting more brightness is increasing. The oxygen is less in here. Carbon is high and oxygen is less in here. We collect this data in between 3 or 4 hours. So for elemental mapping, it's working very well. So we mentioned about the circular polarity of our undulator. Why it's important? It's important for magnetic materials. There is a technique, XMCD, X-ray circular magnetic, X-ray magnetic circular dichroism technique. With this technique, scientists can make magnetic moment measurements. And we have there are two type of samples in this perspective. One sample has in plane magnetization. If it is in plane, the magnetic field, we have to give a magnetic field which is in plane, which is parallel to the surface. For this reason, we have an assembly which is produced in Jülich. And there are some permanent magnets. We can put our sample between these two permanent magnets. And by changing the circular dichroism, of course, we have to give an angle between the incoming beam and the surface normal. And by this way, we can make magnetic measurements. If magnetization of the material is out of plane, we have an electromagnet. We can put our sample on this electromagnet, and we can change the direction of the circular polarization, and we can make an XMCD measurements. And here is the magnetic flux of the electromagnet. We can go up to the 200 millitesla. And in here, you can see the XMCD measurements of the nickel over an magnet, commercial magnet. Our neodymium magnet is coated with nickel. And when we look at the nickel edge, you see when we change the magnet polarization direction, we collect a different intensity in different edge. And when we make a differentiation with them, this is the XMCD measurements. Here is the end of my presentation. Nothing is achieved alone. I want to thank to HESEB project team in the upper part. They always support me, and I want special thanks to Wolfgang Eberhard, Zeynep Öztürk, Ahlam Fahran, and Rolf Folat. They are spending time with me to achieve these things. And of course, my SESAME colleagues, if without them, it's not easy to achieve these measurements or these things. And I want you to thank for your patience and attention.
Thank you, Mustafa, for the nice talk. So we have time for questions. Is there any question from the audience?
Someone has raised the hand
I don't.
in the beginning. In the beginning, I
Yeah,
don't
it was a
know.
mistake. It was a mistake, actually.
Here
So
is my email. You can reach me if you have any questions. I'm kindly invite you to use HESEB. Soft X-ray absorption spectroscopy is not a I don't want to say well known, but mostly people work with XPS. But again, if you are working with catalysis, if you are working with batteries, if you are working with photovoltaic cells, it gives you very nice data about the electron structure, which is important in many, many areas.
okay, so we have some questions in the chat. I don't know, Zakaria, do you want to ask it yourself? Unmute and ask. Okay.
Maybe it's better if you
Yeah.
read.
Okay,
Go
I
ahead.
will read then the question. So from Zakaria Abdel Fattah, what is the error margin in the X MCD spectra in the last few slides? Detection limit?
Detection limit. Okay. Detection limit about the magnetic field strength or elemental. I have to I detection limit about the element. Of course, if the number of element is decrease, the signal will decrease. But if you are asking the magnetic moment, I don't know. But if you are asking me the elemental presence of the elements, less than 1%, the it's getting lower and lower. The detection, I mean, the signals start to become noisy. If it's less than 1%, if your element is less than 1%. But for example, if you are using this one, you cannot make total electron. Actually, it depends also on the fluorescence yield and total electron yield. If it is less than 1%, total electron yield is not working very well. But fluorescence yield will work, but there are some limitations about that. The silicon drift detector, X-ray diffraction, XRF detectors are don't like too much signal. So if there's too much signal from your sample, I mean, if there are interference with others, also it's not good. But we can go maybe 1000
Very much
ppm level.
thank you very much, Dr. Mustafa, for the very interesting talk. Yeah, so my question was related to the spectra itself, the XCMD spectra, and the difference between the two spectra. Yeah, I mean, how one becomes sure. Yeah, because I see the spectra before taking the difference qualitatively similar. I know, of course, they are not identical, but to what extent one can relate these slight differences.
Oh, okay. You are asking about the XMCD, and
Yeah, exactly.
I mean, okay, this difference is coming from the interaction density of state. I mean, in here we are applying a magnetic field on nickel, and nickel d orbitals are splitting, and not splitting. The density of state is changing, and the photons has different circular polarization orientation. So in one case, it's getting interact with the material more. In one rotation, it's interact with the electrons with similar rotation more. If it's less, in opposite rotation, less. So it is the idea. They are the same. They are the same material. These are collected from the same materials, same elements, from the same spot, but just the rotation orientation changed. Circular polarization orientation changed in here. Did you get my point?
Yeah, I think he has answered that he's satisfied. So, so let's move to the next question by Yahaya Mohammad. I'm going to ask you to unmute.
Hello, good morning from here. Good morning. Please,
Hi.
my question is that actually I've been thinking of writing proposal to SESAME, which is ESOP, and I'm very glad to join this talk this morning because you talk about the soft X-ray. But from one of your slides, I realized that the energy it's between 200 to 2000. And
Okay.
I don't know if with this energy, because I know the energy of phosphorus is more than this. I don't know if there is any manipulation you are doing in such a way that I can study phosphorus at KH.
KH, okay.
Because
it's a
I'm
very nice.
working, because
No,
I'm
no,
working on soil.
Okay. Okay, it's very nice. Actually, in here, phosphorus and sulfur are in an edge, in the edge. Either they have L edges at lower, and sulfur is working. Sulfur L edge is working, but phosphorus L edge is it's headache, actually headache. And KH of the phosphorus is in more than 2000, and it's not easy to find in the world. There are very limited number of beamlines which is working with phosphorus K edges, because we call it neither soft X-ray or hard X-ray. It's tender X-ray. It's in the tender X-ray regime. Phosphorus K edges, sulfur K edges they are in the tender edges. In SESAME, there is no any other beamline who can carry these elements. Phosphorus, I mean, when you look at the phosphorus L edges, if it is phosphate, it is not easy to understand it. It is very hump. It's coming very hump and beam, something very hump. Sulfur has some good data in sulfur edges. It gives a very good chemistry about the element, but phosphorus is a headache, to be honest. But in SESAME, we don't have any other beamline. At the end, I strongly recommend you to let's get in contact and make a meeting with you. And when you look at even when you look at the literature, you can see the phosphorus L edges. If it work with you, I'll be happy to get in contact with you and talk with you.
Right.
Okay, thank you.
Yeah.
So the next question is by Ruby Fool. I will ask to unmute. Ruby.
Hello, am I audible?
Can you shout a bit more? I mean, I cannot hear very well.
Okay, I just wanted to know if it is possible to calculate the hole density or the vacant sites through the HESEB.
Could you understand, Nicole?
No, if you can repeat, please.
Please, a bit shout. It's so deep. Your sound is coming from so deep.
Is it possible to calculate the hole density or the defects?
The hole density or the density of defects.
Okay, it's very nice. I forget to mention about it. Yes. Yes. It's yeah. When I'm preparing it, it was in my mind, but I forget to tell it. Sorry. When there is an defect means there is an defect in here. Defect in here, for example. So there's an empty place in here. So if there's an empty place, also specific photons will absorb from here to here. You get my point? So so we can see this in here. For example, in Wells band, we have defects in here. we will have some defects in here. So it will give us an pre-edge. We can see this defect as a pre-edge feature in our sample. You get my point? So also it gives us, if there are some empty orbitals in valence band, if there are some empty states lower than the conduction band, also it gives us this soft X-ray absorption spectroscopy will give us a clue about that. We will see an pre-edge feature before the edge at lower part. Is it okay?
Yeah, I think it's okay. Yes, thank you. Thank you. Very interesting. So the next question is by Ahmed El Kadravi. So please, can you ask the question?
Hello,
Hello?
you hear me? You hear
Yes.
me? Yeah, okay.
Yes.
So my work is on photocatalysis and using a photocatalyst like bismuth vanadate. Okay. So I would like to ask a question about band gap. Band gap measurement is done by using absorption techniques, but sometimes we use UV absorption by using UV visible spectrophotometer. But I mean, here for X-ray absorption spectroscopy, can we use it also for this purpose? And what is what is the efficiency of this? And if I'm using or if I'm doping with a lanthanide, what about fluorescence also? Can I measure fluorescence from my samples using X-ray absorption?
Okay, fluorescence in visible range. I mean, it absorbed X-ray.
Yeah, visible range.
but
Yeah, visible range.
Yeah, photoluminescence. You mean the photoluminescence actually?
Yes.
It's absorbing
yes.
it's absorbing the X-ray and giving a fluorescence in the visible range.
Okay.
Yeah. We didn't try it. Actually, we can do it. Well, how we can do it? Our neighbor, X-ray absorption spectroscopy, XAFS, they have an spectrometer, and we can do this actually. We didn't try it.
Okay.
If you have interest in this, we will get in
Yes.
contact. We will discuss this. We will try to arrange something, and we will try this. Actually, it can be done.
Okay.
We can exposure your sample. We can make an X-ray absorption spectroscopy. And during that time, we can make an fluorescence in the visible range. We can make the fluorescence spectroscopy in the visible range.
Yeah, understand. Okay. Thank you, Dr. Mustafa.
Please get in contact with me. Send an email, and we can make a Zoom meeting. I'll share some data with you about some design about that.
Great. Okay.
It can be done.
Thanks.
It can be done.
Okay.
But it needs some
Thank you.
special work.
Special setup, yeah.
Setup,
yes.
Okay.
Thank you. So we can move to the next question by Samuel Tete. So please.
Okay. All right. Thank you. Thank you for your presentation. I want to know if this technique can be used to determine elements in two different oxidation states. For example, when you are working on redox processes, you can have an element in one state is in +2, and then you add a reagent, it changes to +4 oxidation states. Can we use this technique to do such studies?
Yes, it is. It is not only the oxidation state oxidation state sensitive. It's also sensitive to the conduction band. We are speaking about solids conduction band, but
Okay.
because at the end, it in XPS, for example, you have only one peak for in each. One peak for each oxidation state, but in here also the conduction bands coming into feature. For example, it is, let's say, magnetite, iron 3O4. It has its own special oxidation state. But what its own oxidation conduction band features, the density of states. From that, people are understanding this. But if it is really mixed oxide, for example, how can I say iron 2 oxide and iron 3 oxide, they are together. I'm asking people to let's make an how can I say let's make an reference, bring some reference, for example, iron oxide reference and iron 2 oxide reference, iron 3 oxide reference, and let's compare them. It is the idea.
Okay.
Yeah.
All right. Thank you.
Okay, thank you.
It's oxidation state, but it's oxidation state sensitive, like XPS.
Okay, thank you. Let's take 1 minute for a last question by Gidan Gebremariam, please.
Okay, thank you so much for the nice presentation. I'm a PhD student. The focus of my research work is organic solar energy. So my question to you is that possible to investigate organic molecules using X-ray, soft X-ray, without causing a damage? Because they are sensitive, especially polymers are sensitive to light. Thank you so much.
Yes. In here, you are completely right. The beam damage is the problem in organic molecules. In some molecules, they are not affected from this, or they are not affected that much. But some molecules are affected. What we can do, we can decrease what we are doing in this perspective. We are decreasing the photon density by decreasing the number of photons which is hitting the sample. But yes, so in some organics, for example, people bring some metal organic framework last year. In some samples, they're affected. How we understand it, they change the color, but some of them didn't affect it from this.
Yeah, it causes degradation. Yeah.
Yes, we have to check it before we start the measurements. We have to be careful. You're right.
Okay. Thank you.
Okay, thank you very much. So I think we have to close and move to the next talk. So thank you again, Mustafa, for the
You're welcome.
nice presentation and the